Welcome, dynamics students. In this lecture, we're going to jump from our knowledge of particle kinetics, and that is the movement of a particle or a rigid body, or excuse me, any body at its center of mass under the influence of forces, plus what we've studied about kinematics of rigid bodies in planar motion, and put those together and start looking at rigid bodies in planar motion kinetics. In other words, how a rigid body that's undergoing only planar motion is going to move when subjected to forces and moments. So what we learned in our study of particles was that a rigid body's mass center, or a real particle, meaning something that has no size, can be described merely by its velocity and position and acceleration and velocity. You only need to know three things. So kinematics for particles or mass centers was just restricted to, the motion of a single point, literally. However many coordinate systems you needed to describe it, still you're really tracking the motion of one point. And we related or we extrapolated those equations of motions for a true particle, something with no size, it's very small relative to the scale of the problem, to the center of mass of a rigid body, provided that that rigid body was undergoing translational motion. So what we never allowed up till now was a rigid body to rotate, especially around its own axis. So that's what we're really going to tackle at this point. And for that, we're going to need Euler's second law, which involves what's known as the moment of momentum, otherwise known as angular momentum, and that was the capital letter H, meaning the angular momentum of a rigid body. We saw a capital letter L, the linear momentum of a rigid body, earlier when we were deploying Euler's first law to relate motion of the center of mass of a body with translational motion. So now we need the angular momentum in order to deal with a rigid body's own rotation. Okay, so I'm marching down through my notes and taking it step by step here. So the moment of momentum, otherwise known as angular momentum, capital letter H, is very useful in a rigid body, a tool to have to deploy force, moment versus motion, because all we need to know in order to calculate it is the velocity of any one point on the body, any point, plus that body's own angular velocity relative to some inertial non-accelerating reference frame. Two pieces of information. So basically omega for the body plus the velocity of any one point. And so we're going to use a real easy figure here to just get an idea of how we use that. So say we have a rigid body out here in space. And note, we're going to the term rigid body now. Back when we were deploying Euler's first law, back in our particle kinetics studies, we basically we used that irrespective of the body's rigidity. So that was applicable for fluids, deformable bodies, anything. Now we are requiring the body that we're looking at to be rigid. That's why we only need to know the velocity of one point and the body's its own angular velocity. If the body could undergo strain, for instance, then we wouldn't be maintaining that constant separation between all points in the body, and none of this would be valid. So now we are definitely limiting ourselves, now that we're jumping into Euler's second law and we're applying kinetics to rigid bodies, or to rigid bodies in planar motion. We have to remember no fluids, no deformable bodies, or at least nothing that is significantly deformable. So things that are practically rigid. So we have a rigid body, body B, out here in space, and we can reference its motion to some origin point here in an inertial reference frame, and I've drawn that looking like it's another little rigid body here. So this is our reference point O that is not accelerating from the standpoint of the problem. So somewhere else out in space we've got point P and maybe it's moving. And we can define, just for giggles, the angular momentum of this rigid body with respect to P. So remember, now that we're going to angular motion, we have to define with respect to what we are rotating. We saw this in particle angular momentum, where we looked at the radius from the axis of rotation to the point of travel of a particle, and we actually defined h for a single particle in those terms. So we're going to see that again in this derivation. That will fall out of it, but we're also going to take into account what the rigid body is doing with respect to its own center of mass. So we have point P, and we've got this rigid body, and we want to define the angular momentum of the rigid body with respect to point P. Well, there's a lot of different bits of mass in that rigid body, and they are all at a different radius from the point P. So we know that angular momentum can be defined as the radius crossed into, and that's the vector cross product, the linear momentum of a particle. We learned that with our particle studies. And we can just add that same relationship up over all of the mass bits in this body. So we're going to define the angular momentum of this rigid body B around this point P as just the sum of the angular momentum of all of the little mass bits in the body, each with their own radius, crossed into that mass bit's own linear momentum. So we're basically doing something similar to centroid and things like that. We're taking something that is small enough, the dm, that we can approximate as a particle, and then we're just adding up the effect of all of those particles' angular momentum into the whole bodies. And again, the r is basically what makes this angular momentum specific to point P, because each of those mass bits is going to be referenced with this radius vector. And this velocity for the mass bit in question is being referenced to our inertial reference frame. So just a quick look at this formula tells us that the angular momentum of a rigid body is going to be dependent on what point we're taking it around. If this point were way over here, that radius vector would be much longer to pretty much all the points, and so we'd probably get a different number. And also the mass distribution. If we had a non-homogeneous body, a non-homogeneous density, so maybe the density was 10 times greater over here, that would definitely change our dm cross r, and certainly also a non-uniform velocity. But the velocity at every single point on that rigid body is the same because it's a rigid body, so we never have to worry about a non-uniform velocity. That's why we only need the velocity of one point, because the body is rigid. Okay, well, that's great. This has gotten us similar in a similar situation that we were looking at particle angular momentum. Now we've just basically integrated the angular momentum of each particle in the body over the whole body. What if we wanted to do that around the body's center of mass here? So we have point C, the center of mass of that body, because generally speaking, the center of mass allows us to simplify things. And so let's look at how we would, I'm going to erase some of things we're not using now. Let's take a look at how we can use the properties of integrals to define the velocity, define the angular momentum instead of about some arbitrary point P outside the body, but around the body's center of mass. So we can define a radius vector from the center of mass to any mass bit. We did that when we were calculating centers of mass and centroids if we used volume instead of mass. And then we can use some vector algebra and say, oh, hey, look, I can add vector B and vector RPC and get vector R. And vector RPC is the radius vector from that arbitrary point outside the body to the body's center of mass. So I can basically substitute this in for R. And then break up the integral into the integral of a sum. So now we're going to end up with the integral over the whole body of the radius vector from some arbitrary point to the center of mass plus the radius vector from just the center of mass to every point in the body, crossed into velocity of those points, which are going to be the same, dm. So that allows us to deploy sum of the integrals equals the integral of the sum, and we can express that angular momentum of the rigid body at any point to the angular momentum about its center of mass plus this integral term where we just integrate the distance or the radius vector from whatever that arbitrary point is to the center of mass crossed into the linear momentum of any given point. So we can basically bring, if we have a constant radius here, we can bring it outside of the integral and then express the single linear momentum of the body based on its center of mass, which is a single number. Okay, so we end up getting that here on the second page, that second term in our expression, because this expression, the integral of the velocity of points over all mass points in the body, this is just the linear momentum of that whole rigid body. That's Euler's first law. And we're looking at the radius vector from our arbitrary point to the center of mass. Well, that's not changing. The center of mass is where it is. So this is a constant, and this just simply becomes, this is our linear momentum for the whole rigid body, capital L. This would be symbol lowercase p for a particle, I believe. So now we have angular momentum of a rigid body about any arbitrary point is the angular momentum of that rigid body around its own center of mass plus the radius vector from whatever arbitrary point you're taking the angular momentum about to the center of mass crossed into the linear momentum for that rigid body. So this part is very akin to what we had for a particle, and in fact this is the expression for the angular momentum of a particle around some point p. So now we're adding the fact that we have something rotating about an arbitrary point, plus it can be rotating about its own center of mass. So we've picked this term up, and this is the big differentiator between rigid bodies in planar motion and just points or centers of mass. And as a note, the line of action, remember the linear momentum is a vector, and its action will be through point C, so through the center of mass. So when we're looking at the way a body might be like orbiting something, not rotating on its own axis, you're going to draw this vector. You're going to execute your cross product around a single point at the center of mass. Okay, let's do one variation on that, and let's move that arbitrary point that's outside of our rigid body that's rotating and moving around in space. Let's move that inside the rigid body itself and see if we can't work out some useful expressions that we can deploy. Because so far we've just basically related the angular momentum of a rigid body around its own center of mass to the angular momentum that results from that body's center of mass rotating about something else. So let's pull that point P inside the body and look at how it rotates about something maybe inside itself that may not be the center of mass. So this schematic is a big rigid body here. This is the outline of the body. I'm drawn in red. And this plane here that has the kind of the faint cross hatching, this is our reference plane. We've kind of sectioned the body here. And so this plane in here is what we call our reference plane from the standpoint of rigid body planar motion. So we've identified, here's our point P that we're gonna write expressions for angular momentum around, and it's serving kind of as the origin for its own coordinate axes. So we've now got a reference set of coordinate axes xp hat and yp hat here in this plane. And so that's now, those have the cross-hatched axes indicating that there are reference axes. We got the center of mass over here, which is not a point P. We can draw a radius vector from P to C. And we have point Q, some arbitrary other point somewhere else in the body that we might be interested in. And we know that because we have a rigid body, that any mass point anywhere in the body, like this dm out here at xyz, where z is not 0, z is 0 in our reference plane, this mass point is going to move in lockstep with point q. So its xy motion is going to be exactly the same as q. That's because that's one of the characteristics of a rigid body that we discussed back in our kinematics. So, important points. B is rigid. So the velocity of our point dm, somewhere out of the reference plane, is equal to the velocity of point q. P and q are in the same reference plane. So now we're going to move forward. Okay, they're in the same reference plane, they're in a rigid body. Hey, we defined all kinds of cool expressions for relating velocity at one point of a rigid body with respect to the other based on that body's angular velocity. So remember you can remember those expressions from the kinematics of rigid bodies section. Spent a lot of time using them, so we'll just apply that here. And we know that the velocity of any point on the rigid body is equal to the velocity at some point that presumably you know, plus the angular velocity of the whole body with respect to some external frame. And that angular velocity will have a point, or will have a vector normal to the reference plane, so it's sticking out in the z direction, k hat, crossed into the radius vector from the point you're looking for, or the point you know, to the point you're looking for. So r p q. So this is a relationship between velocities of two different points on a rigid body. We can deploy those for this rigid body. Okay, so let's put that in for v, and we'll look at an expression for r, and let's apply this term to get an expression for angular momentum referencing a point that's inside the body somewhere. So we're going to start by using this vq, which is like v at any point, in here for our velocity at any point. And then we're looking at the radius vector from a known point to that mass point anywhere. And that we can just express as xp, yp, zp, because basically p is the origin. So, you know, our mass point is going to be located at some distance xp, yp, zp. So that's the radius vector from our point P. So we can express that just like this. Basically, it's the radius from our origin within the rigid body. And then we're going to use our expression for, because we've got a radius vector in terms of point P, we're going to be referencing to this, and then we're going to use this whole expression for that velocity. Okay. So this is what our expression for our angular momentum of the rigid body about point P, where P is inside the body now. So here's our R, which is just some location point of our point P, and that we can use to identify, from this we can use to identify any other point. And we're crossing it into our velocity at any point expression here. So Vp plus the angular velocity of the body crossed into rpq, because we've defined q as having some xy coordinate with respect to p. And we can rearrange that integral basically distributing r over this term and then the next set of terms. We've got a sum in this term, so we can distribute the cross product. The cross product is distributive over sums. And the first term, we end up getting r cross Vp integrated over all the mass in the body. And we know that this first part of that equals the mass, the total body's mass, times the radius vector from P to the center of mass. So this is like this is the numerator in our definition of center of mass. And then we have the second set of terms, which we'll need to look at a little bit more closely to get something useful. So just revisiting our integral of our radius vector from point P integrated over all the mass. We just have the whole body's mass times the radius from P to the center of mass. And we remember that our angular momentum is the same, or excuse me, our angular velocity, omega sub b, it's constant and uniform over the whole body because it's a rigid body. So now we can use this relationship and the fact that this is a constant. We pulled this term out of our integral up here. It would have ended up getting multiplied by all of these terms. So if we multiply all these cross products out and then we factor out our angular velocity of b, we end up getting this expression. And now we have something that we can actually start deploying in problems. So we've now, what have we done? We've still got this h sub p. We've defined the angular momentum about a point P of a rigid body where P could be inside the rigid body is the radius vector from point P to the center of mass of the body crossed into the mass times the velocity at the point of interest in the body. So that's that 1 point plus the angular velocity of the body tells you everything about its motion. So we're setting up around, maybe we knew what the velocity of point P was with respect to an inertial reference frame. We could probably calculate the mass of the body if we had a density function. We knew something about its geometry we could integrate. We could probably also get the center of mass location, our RPC. This is all stuff we would probably know. From that and some knowledge about the angular velocity of that body, we can get an expression for angular momentum, which we will then leverage to relate to the sum of the moments. So we're setting up for our link back to forces. So far we've just been talking about kinematics. We've just been talking about motion and introducing this idea of angular momentum of a rigid body. This chapter is kinetics, so eventually we need something that we can relate to force or moment. So we're very close now. So we now have an expression of things that we can calculate easily about the rigid body. And then we have these integrals that basically tell us something about mass distribution. And if you are familiar with moment of inertia from your statics study, you should probably recognize at least this one. This is the polar moment of inertia, which is basically the sum of the moment of inertia about the x-axis plus the moment of inertia about the y-axis. But by putting these together and squaring them, we have an r squared, which is a lot more useful, especially for axisymmetric bodies. And then we have these two terms, which are the products of inertia about the xz axes and yz. So these are characteristics of the body itself. They don't really have anything to do with its motion. These are our analogs to mass in linear translational motion. We have 3 of them instead of just one number. But now that we have things rotating, we need to know a lot more about how that mass is distributed with respect to whatever axis we're rotating about. So there's 3 terms. And what we'll find as we go on is these last 2 terms, when we are working solely in planar motion, they go away. They also go away for certain symmetry conditions, even if you're in general motion. But for the purpose of our planar motion discussion, we're going to show how these end up not being something we need to worry about, because we can't have the sum of any moments out of the plane of motion being non-zero, or we wouldn't have planar motion. We'd start moving out of that plane. So let's just go through some definitions, because this is our powerhouse statement that'll lead back to force. So these integrals are called the inertial properties of our rigid body. So we have our IZP, which is our z-axis. Is pointing, it would be directed in the z-axis moment of inertia about point P. This is our polar moment of inertia. And then we have our two products of inertia, which can be thought of as the product of inertia of a mass with respect to two different axes treated separately. So you integrate with both. But again, it's with respect to that point P. So if our point P is at the center of mass, or if the velocity of our point P is zero, like for a fixed pivot, for instance, or if all of our motion is rotational about the center of mass, or something, again, a fixed pivot would be a good example, then our first term is zero, and our angular momentum is only a function of the rigid body angular velocity and the inertial properties. So we just basically, if we're at the center of mass, then RPC is zero. And if our point P that we're taking the angular momentum about is zero, like it's fixed, then our entire angular momentum of the rigid body with respect to point P is simply due to the body's own rotational velocity and its inertial properties, which simplifies that. So we get just this expression. And this is the expression above with the integrals collapse down to just their products and moments of inertia. So we have our polar moment of inertia here, and then our two products of inertia. Okay. We're gonna take a pause here because we've covered a lot of theory. In general, you won't be leveraging these real fundamental derivations and proofs all that much, but it's very important to know where we got our expressions for angular momentum of a rigid body, and more importantly, what were the constraints. The biggest ones being you have to stay in planar motion in order to be able to consider the motion that we have in our proof, and you have to have a rigid body. And beyond that, other big points are we have shown how the linear momentum of the entire rigid body and radius from our point of interest to the center of mass relate to angular momentum. And then we've leveraged our very handy velocity at any one point in a rigid body to any other point, like a known point, to create an expression for angular momentum of that body at any point, and in so doing derived our expressions for our inertial properties, our polar moment of inertia and our products of inertia. So in the next lecture, we're going to go over a little bit of practice calculating moments of inertia. I'm going to give a very brief discussion of products of inertia because we won't be using them to any great extent for planar rigid body motion, and then dive into some applications, putting this theorem to work.